Quantum computing. You've heard the term, right? It promises to change, well, pretty much everything, from medicine to finance. But let's be real, it's also surrounded by this huge cloud of hype and confusion. So today, we're going to cut through all that noise, separate the science fiction from the science fact, and figure out where this incredible technology really stands.
And you know, it's easy to see why the hype gets so out of control. As futurist Bernard Marr puts it, the ideas themselves are just wild. We're talking about particles being in two places at once, or instantly connected across the universe. It is seriously mind-bending stuff, and that's the perfect breeding ground for myths to grow. So let's just tackle the biggest one right off the bat.
Okay, let me be super clear. You are not going to be buying a quantum MacBook anytime soon. Think of a quantum computer less like a new brain that does everything, and more like a specialized coprocessor. It's an incredibly powerful new tool in our toolbox designed to work with our classical computers to solve a very specific kind of problem that's literally impossible for even the biggest supercomputers today.
To really get to the bottom of this, here's our game plan. We'll start with hype versus reality. Then we'll dive into this critical noise problem that holds things back. After that, we'll look at the first real quantum advantages we're seeing today, explore the global race that's heating up, and finally, look at how we're building the quantum future.
Okay, let's dive right into our first section. Why isn't a quantum PC on the horizon? Well, it all comes down to the fundamental nature of the quantum world itself. It's unbelievably powerful, but it's also incredibly fragile.
The number one enemy of any quantum computer is something called decoherence. Here's an analogy. Imagine a qubit's quantum state is a perfect, delicate whisper. Decoherence is like trying to hear that whisper in the middle of a roaring football stadium. The slightest vibration, a tiny change in temperature, basically any interaction with the outside world, and that whisper is just gone. The quantum information vanishes, and you're left with errors.
And trying to manage this fragility creates these massive engineering hurdles. It's why today's machines are called NISQ computers. That stands for Noisy Intermediate Scale Quantum. And that noisy part is key. To keep that environmental noise down, they need extreme cryogenic cooling. We're talking colder than deep space. Even then, controlling the qubits is really, really hard. And we still don't have the robust error correction that would make them truly fault-tolerant.
So, if today's quantum computers are so noisy and prone to errors, what's the point? Well, researchers aren't trying to build a perfect machine just yet. Instead, they're focused on finding places where even a noisy one can get a win. And this is where the real progress is happening. The goal for the near future isn't some kind of quantum supremacy where they take over everything. It's about achieving something called quantum advantage. This is all about finding those very specific needle-in-a-haystack problems, where even a noisy, imperfect quantum computer can do something that the world's most powerful supercomputers just can't. And finding that advantage is a really methodical process. First, researchers have to identify a problem, like, say, simulating a complex molecule, that just gets exponentially harder for a normal computer. Then they design a very specific quantum algorithm for it, run it on the actual hardware, and then, and this is the crucial part, they have to prove it actually delivered a meaningful improvement. It's not enough to be different, it has to be demonstrably better. So, where are we seeing this in action? Let's look at the first real-world applications that are starting to pop up right now. This is where the hype starts turning into some pretty tangible results.
This slide gives you a great snapshot of the key battlegrounds. Let's take molecular simulation. A classical computer really struggles to accurately model a complex molecule because of all the quantum weirdness going on. But a quantum computer? It's literally built to speak that language. This could let us design new drugs or materials atom by atom, instead of the trial and error we do now. It's a game changer.
So here's the key takeaway. These are not tasks you'd ever do on your laptop. These are massive, high-value challenges for entire industries. Solving just one of these problems could lead to breakthrough medicines, way more efficient global supply chains, or more stable financial markets. The potential impact is just enormous. And that potential for massive impact? Well, it hasn't gone unnoticed. It has absolutely ignited a fierce global race, turning quantum technology into a whole new arena for geopolitical competition and strategic investment. And this chart, wow, it basically reveals the new map of global innovation. China and the US are just dominating, accounting for over 80% of all quantum patent families combined. Owning these patents means owning the foundational building blocks of the quantum future. and that gives them a huge strategic and economic edge.
And it's not just about the patents. It's about the money pouring in to make those patents a reality. According to a McKinsey report, quantum companies in the EU attract 10 times less private investment than companies in the US. That's a staggering gap. And it really highlights the aggressive, fast-moving investment culture that's driving the American quantum ecosystem forward.
So, with this intense global race as the backdrop, how do we actually get from today's noisy machines to a truly powerful quantum future? Well, there is a strategic roadmap taking shape for the next decade.
This diagram shows a really smart, holistic strategy. The EU, for example, isn't just betting on computing. They're building an entire ecosystem around 4 pillars: computing, simulation, secure communications, and sensing. This shows that the future isn't just one magic box, but a whole network of different quantum technologies working together, all built on a solid foundation of basic science and education. You know, the long-term vision isn't just to build a bunch of isolated quantum machines. The ultimate goal is to connect them, to create a quantum internet. Imagine a network that can transmit pure quantum information between computers, simulators, and sensors. It would unlock capabilities that are just impossible with the internet we have today.
So we've gone on this journey from the myth of the quantum laptop to the reality of the noisy, specialized processor. We've seen the first real-world advantages and the global race they've kicked off. We know what the building blocks for the future look like. But that leaves us with one final and really exciting question. What's going to be the true killer app of the quantum age? The application we haven't even thought of yet? That's the discovery that still lies ahead.